Strategy games, a common pastime, but not one without a mental challenge. Even the most basic of strategy games can be tough to master. Today, we'll dive into some of the simplest games you could possibly imagine and see that strategy is really not as simple as it might seem. Let's play a game called Wit Queens. I have a quarter infinite chessboard that extends forever down and to the right. On one of these squares is a queen, placed at a random square to begin with, and the queen may move to the left, up, or diagonally, any number of spaces. We take turns making moves, and the player who gets the queen to the top left square wins.
Well, that doesn't seem too hard.
Great. Would you like to go first?
Sure. Let's see. It's pretty clear that I don't want to move all the way to the top or left, because then you can win right away. But I also want to get close to the corner so that I'm closer to the winning corner, right? So I'll move here.
Interesting move.
If I move here, I lose. If I move here... But if I move here, I also lose? Darn. Maybe I was just unlucky. Or perhaps this is an unfair game and the first player loses no matter what. Let's try again. I'll go second this time. This isn't working out. Maybe the strategy for this game is more complicated than I thought.
Yes, this seemingly simple game is not easy to win if you don't know what you're doing. But with a bit of mathematical thinking, we can break this game down and figure out the optimal strategy.
Mathematical thinking?
Yeah, if you just simplify your problem, use systematic logic, and make generalizations, you can win many games.
Great, how do we get started?
Before analyzing Wit Queens, it will be helpful to think about an even simpler game to help us develop a strategy for creating game strategies. I know, a strategy about strategy. It sounds crazy. Let's consider a simple subtraction game with marbles. Two players start with a pile of some number of marbles. They alternate turns, taking one or two marbles on each turn. The first player who is unable to move loses. If that's confusing to think about, think that the last player to take marbles wins. What is the strategy for this? To figure it out, we'll start with the easiest game states and work our way up. Let's say the players are you and me. Suppose it's my turn and there are 0 marbles left. Then you win because I can't move. If there's 1 marble left on my turn, then I can take it and you lose. What about 2 marbles? Similarly, I can just take both marbles. But what about when we get to 3 marbles? I can't take 3 marbles in one turn, so you'll get another turn. If I take 1 marble, there are 2 marbles left on your turn, so you are in the position I was in the 2 marble game. That means that you can just take both of the 2 marbles and win. If I take 2 marbles, then we're in the 1 marble game with you going next. So you take the marble and win. This means you are guaranteed to win. So we have found 2 types of game states. States where you are guaranteed to win, and states where I am guaranteed to win. This gives us the concept of P and N positions, which make talking about this complicated logic easier. An N position is a game state where, if both players play optimally, the next player to move will win. A P position is a game state where the previous player to move would win. So in our game, 0 and 3 are P positions because I was going next and I had no way to win, and 1 and 2 are N positions because I was going next and was guaranteed the win as long as I made the correct move. Let's keep looking at the positions. If there are 4 marbles left, taking 1 leaves me in the 3 position with you going next. That means, like me earlier, you are in a position where you cannot win. So 4 is an N position, because I was the next player to move, and I have a guaranteed win if I choose to take 1 marble. With 5 marbles, I can just take 2 marbles to get it to 3, so that's also N. What about 6 marbles? Both of the possible moves, taking 1 or 2 marbles, will put me in a position where the next player gets the win. But after I move, you become the next player, so you are guaranteed to win, which means that 6 must be a P position. This method of looking at each possible move and seeing what type of position we land in relates to an important formulation of P and N positions. An N position is one where you can move to a P position in one move, like with 4 or 5 marbles. This makes sense because after I make a move, I become the previous player to move, and if I'm in a P position, that means I get a win. A P position is one where you cannot move to a P position in one move, like with 6 marbles. This says that we don't need to go through complicated chains of logic to classify positions, because all we care about is P versus N. We can just look at each possible move and see where they take us. So from 7, we can get to 6, which is a p position, so 7 is n. From 8, we can also get to 6, so that's n. But when we get to 9, we can no longer move to 6 marbles in one move. We can only move to 8 or 7, which are n positions. So 9 is a p position. If we keep going, the pattern becomes clear. We can see that the p positions are the multiples of 3, because 3 is the smallest game we cannot win, and we can force our opponent into the 3 position only when we don't have a multiple of 3 marbles. From this very simple game, we have seen that some games have scenarios in which one player, if playing with optimal strategy, is guaranteed to win. In the subtraction game, that means always moving so that a multiple of 3 marbles remains. That's because the multiples of 3 are p positions, which means that the previous player to move, which is you after you make that move, has a guaranteed win with optimal play. Now we have a general framework for analyzing games. We look at the simplest possible game states, determining if they are p or n by considering all possible moves. Then we extend the analysis to more complex positions by looking at the possible moves and seeing whether or not we can get to a p position. Lastly, we often try to find a nice pattern in the p positions. We can apply this exact framework to wit queens. Suppose the queen is in the top left corner. Then whoever just went wins, per the rules. That means that this is a p position. But that means that we can reach a p position in one move from every other square in the top row, in the leftmost column, and on the main diagonal, so all of those are n positions. So now let's look at the 2-1 square. We can move left to n positions, up to n positions, or diagonally to n positions, but there's no way to get to a p position, so the 2-1 square must be a p position. We can apply the same argument to see that 1-2 is also a p position. Those two p positions give us another batch of n positions just by using the fact that any position where we can move directly to a p position is an n position. What are the next squares that aren't filled in? The 3-5 square and 5-3 square. A quick check shows us that we can only move to n positions from these squares. So these are p positions, and we can keep going.
Okay, so now we can see that we can't make a move to a p position from the 4-7 square or from the 7-4 square, because all of the squares we could possibly move to are n. That makes those two squares p.
Right. Let's look at it a bit more.
It looks like the p positions form two approximate lines.
Indeed. We can describe these lines as k times phi squared, and k times phi squared, k times phi, for any natural number k, where phi is the golden ratio, a number that's found very commonly in mathematics and nature. Try extending what we did here and see if your p positions have the coordinates described by these formulas.
So if I'm playing this game, I just need to calculate the p positions using these formulas and move to one of those squares on each of my turns.
Yep. The concept of p and n positions is key to analyzing many simple games like subtraction games and wit queens, part of a class of games called combinatorial games. The strategy games you play in your free time probably have many more elements, and you won't be able to classify positions as p or n, but you can still use the organized logic we used here to create successful strategies.